Yeah, it seems no one so far is joining apart from you, which I guess is fine. We'll see. Uh, Hopefully, there will be at least one or two more people. Um, I have not looked at the problem at all before today, and everything up to today, I just completely half-assed. Like I got the stars, and then just that's done. Uh, and my hope slash plan is to do a bit more like to pretend as if we actually the quality code to a degree. Like probably start just getting the stars and then uh, attempt to improve on it over time. We'll see. But let's just start by having a look. As the flight slowly drifts through the sky, the elves at the mythical. Do you, by the way, have you done Advent of Code? Oh no, smooth streaming. God damn it. Okay, let's hope that this works better. We will see. I don't know. YouTube is still complaining. Now it's complaining that the resolution isn't high enough. I don't know. Okay, this is just annoying. Let's see. The elves at the Mythical Information Bureau at the North Pole contact you. They'd like some help debugging a malfunctioning experimental energy source about one of their super secret imaging satellites. The experimental energy source is based on cutting-edge technology. Set of Conway cubes contained in a pocket dimension. Now I want to know what a Conway cube is. When you hear it's having problems, you can't help but agree to take a look. It's still buffering, at least for me. Anyway. The pocket dimension contains an infinite three-dimensional grid. At every integer three-dimensional coordinate, there exists a single cube, which is either active or inactive. In the initial state of the pocket dimension, almost all cubes start inactive. The only exception to this is a small flat region of cubes, your puzzle input. The cubes in this region start in a specified active or inactive state. 3D grids, that's annoying. The energy source then proceeds to boot up by executing 6 cycles. Each cube only ever considers its neighbors. Any of the 26 other cubes where any of their coordinates differ by at most once. For example, given the cube at dart, its neighbor included the cube at what? Yeah, okay, that's fine. During a cycle, all cubes simultaneously change their state. Okay, so this is the same as the Game of Life thing they did earlier. If a cube is active and exactly 2 or 3 of its neighbors are also active, the cube remains active, otherwise the cube becomes inactive. If a cube is inactive, but exactly 3 of its neighbors are active, the cube becomes active, otherwise the cube remains inactive. The engineers responsible for this experimental energy source would like you to simulate the pocket dimension and determine what the configuration of cubes should be. For example, consider the following initial state. Even though the pocket dimension is 3-dimensional, this initial state represents a small 2-dimensional slice of it. Okay. Yeah, okay, I guess. So what's annoying about this is that the grid is infinite. So how are we going to model this? Yeah, so the problem is relatively simple to understand. It's just a three-dimensional cellular automaton. Just the grid is infinite, and we don't know how to best simulate that. Let me think. Yeah, if it was final, it would be simpler. It's just basically an array, maybe a three-dimensional array. We could do just maintain a list of all the active cubes, but that would be that wouldn't even be that hard. We can just use a map. Yeah, I think that should be fine. Let's try that. Okay, so oops. Oh, I should actually go to the correct subdirectory. So my idea is we let's first like read the input. That should always be the first thing. And the way we will model this is to say we will just have cells which are three-dimensional vectors, I guess. And then we will just have basically a set of live cells. And that's basically all. And we will just start at some arbitrary point. So the input, just to see what oh, that's a small input. Cool. So the way we will do this is we will just read line by line. And then like the first line, the first character will be 0, 0. Or 0, 0, 0, 0, I guess. And then we will do for IB range s dot bytes. And then set the cell. So the cell is going to be a cell. The first will be the line number, which we should actually collect. The second will be the column number, and the third will always be 0. And then we will say, wait, actually we can do this here. If b equals dot, I think dot is what is used for, yes, for dead cells. Then we will just continue. Otherwise, we will add the cell to the grid. By the way, if I should, I can enable syntax highlighting just for that. And I guess that's it. And I think this is a decent representation for the grid. We can even like do this. And now we will have, we would just have a basically a set that lists all the live cells. Now the next step is to simulate the grid. There are in place, so we can return a copy. And I think for things like this, doing the copy is easier because you need to actually know what the state of the grid was before if you want to count the neighbors. Like if you do it in place, you might swap a cell even though you later need to count it as a neighbor. So we will just the grid and return a new grid. And the rules are, if a cube is active and exactly 2 or 3 of its neighbors are also active, the cube remains active. Otherwise, the cube becomes inactive. If the cube is inactive, but exactly 3 of its neighbors are active, the cube becomes active. So for every cube that changes state, either the cube itself or one of its neighbors will be active, which is interesting because like we can't iterate over inactive cubes, but we can iterate over active cubes and then look at them and look what like happens in their neighborhood. So let's do that by making a new grid and iterating over all the cells in our old grid. So the first thing we do is we look at if we iterate over it, it's obviously an active cell. So we will take that and look at all its neighbors. Let's do that as a method. Let's just like write a general method for visiting all the neighbors of a cell, of a given cell, because that will we will definitely need that multiple times. And we will do. Do we want to iterate over the neighbors or do we want to iterate over the neighborhood? We will iterate over the neighborhood. So we will include the cell itself in its neighborhood. And this seems a bit dumb, but let's see. Call. Wait. I don't know. Cell 2 is the cell, but is a cell that has as the first coordinate it will have C0 plus I. C1 plus J and C2 plus K. So basically we will take like in all 3 dimensions we will take -1, 0 and 1 and add it to each cell. And then just call F with that. And then we can say, I don't know, count the neighbor cells and do a walk neighbors of the cell we are currently visiting, which is an alive cell. And we will just the cell actually needs to obviously the cell doesn't just need to have coordinates. Yeah, exactly. We walk all the neighbors and we see if they are alive. So we will look at if G of the cell the neighbor we are walking. So if the neighbor is alive, we will increase n, and now n should be the number of alive neighbors. And if that number is if this number is 2 or 3, then the cube remains active. So if n is 2 or n is 3, the cell remains active. So it will be in the next grid. Okay, so this is we have a cell that was active, and we have now correctly changed its state to, or like left its state at active. And of course, like obviously, if the number of alive neighbors is different, we will not add it to the next grid and thus not change, like it will automatically become inactive. Now the next thing we want to do is if we want to check if the cube itself high fribbledom. If the cube itself is inactive, but exactly 3 of its neighbors are active. So now we are still only like, now we actually need to walk all the neighbors and check for each neighbor if it's inactive and this condition is true. And we can actually just like, we already look at all the neighbors and check if they are active. And we can just add another helper to make the code easier. That just does exactly this. We can actually remove this. And return n, which makes the code easier. Where is it? Am I blind? Ah, here. Of the cell we are looking at. So the code should be exactly the same as before. Just now we have a helper. And we can do a, oh, actually we now have to count them again because we lost access to the closure. Anyway, then we will just do that. That's fine. Walk neighbors of the cell. Let me know, by the way, if I'm not explaining things well enough or whatever, right? Okay, so now we want to check if the neighbor cell, there's one thing we actually need to do, is if we count the alive neighbors, we actually need to say, we need a second variable. Because in walk neighbors, we do include the cell we are looking at, but we are only interested in the cells that are not the cell itself. We can also just skip it here, to be honest. And then we don't have to care about it in here, because I think we basically never want to look at the cell itself as one of its neighbors. Which means we can continue to override, to shadow this variable. Okay, cool. So next we want to look at all the neighbors, check if they are alive. If the cell is, we are looking at if the neighbor is alive, we already will visit it eventually in this loop. And so we don't have to look at it again. So we will actually say, if it's alive, then we don't care about it. We will just return. Oops. However, if it's not alive, then we want to count the alive neighbors of that. Of the neighbor cell. And if n is, let's see, exactly 3, then it should be marked as active in the next iteration, right? So like we might mark a cell as active twice or whatever if we visit it multiple times, but that's fine, whatever. And this should actually guarantee that. So if I'm not mistaken, this should, it should compile. It doesn't, because I'm in the wrong directory. It doesn't. And walk neighbors, typing is hard. How now I don't feel confident how to actually write this, spell this. And grid is declared but not used. Yeah, that's true. So let's just say, let's see, when do we stop? What's the stop condition? Simulating the active cell in each cycle after the full 6 cycle boot process. Wait, is that defined that we always simulate 6? Yeah, okay, apparently. So we will just do a, let's actually, this is going to be annoying. How do we dump the grid so that we can actually look at it and see if it's doing what we expect it to do? How is it represented here? In this manner. Ooh. This does not necessarily bode well for us, because we have no idea what the minimum and maximum dimensions of our grid are. We could do this efficiently, or we could do it lazily, and I will start with the lazy thing, and then we have space to optimize later. We will just return a function that, let's just say cell, that will iterate over the grid and like take the maximum rectilinear that contains all alive cells, and that's slow, but whatever, let it be slow. Then we at least know like what the interesting part of the grid is that we wanna output. So let's do this and say if C0 is less than min 0, then min 0 is C0. This is so annoying. If C0 is greater than max 0, max 0 is C0, and then we will triplicate this and and now we should have this. Does it build? Nope. Why doesn't it build? Oh, because we are iterating wrongly. And like later we can if we want to optimize that, we can just keep that updated while we add cells. Like we will just, instead of having the grid be a bare map, we will just make it a struct and add a bounds, and then whenever we add a cell, we will update the bounds. But for now, let's say this is fine. So let's say is grid.bounds, and then we have now we iterate over all the over for z equals min 2 z less or equal than max 2 z plus plus. This should be a method. Grid dump, I don't know. So as to not pollute our namespace. Not our main namespace, our main function basically. And then we will printfen set equals that, and we will iterate. And I am, for the record, I am unhappy with myself for mixing abstractions here. Like previously I used I, J, and K for indices, like for the coordinates, and now I'm using X, Y, Z. But I need to keep it clear in my head which is which, and so for now I will just do this, and then we will look at it and make it readable at a later time. For the record, I'm adhering to the advent of code modification of Rob Pike's 3 principles, like 3 steps of like make it correct, make it beautiful, make it fast, in that order. And I will add a 0, like get the stars. So let's do this. Oh, this is really ugly. We're also like iterating in the wrong order, but that's the thing we want. Max 1, min 1. Y plus plus. Fim.print if grid cell xyz, then fim.print a hash, otherwise fim.print a dot, and that's that. And oh, we actually need to swap these around. Fim.println, so this iterates over like 1 row in the grid. This is per row, and now we will add a new line before the next Z layer. And so let's dump the grid. Let's say grid is oh, actually, if we are using methods anyway, why not do that? And this should do something. I'm not sure what it will do, but grid.bounce. What? Why? Not grid.bounce. This. And the way I usually do these things is I first input the example, and then we will see whether this does what we want for the example. Let's do a side-by-side comparison. This looks not like what we want. We did something wrong. So we will figure out what we did wrong, hopefully. Okay, so this looks very wrong. This is not the starting state of the grid. I did something horribly wrong. But what? And then also we have like -1 and oh. Okay, so this is obviously wrong. Let's see, is this wrong? We can check. Also, we can like just test. What happens if we just do this and like? So printf debugging. Let's see. Does not contain what? Does not contain day 17, 17. Wow. Does not contain package day 17, 17. Yeah, but like you're not supposed to do. Oh, this is the problem. Okay, so it says 000 is true, 010 is true, and 020 is true. So there are 3 alive cells. That's not enough alive cells. So first problem. Not enough alive cells. Why not enough alive cells? So these need to be swapped. Let's actually do this now while we're at it. Oh, this is what we did wrong. This is one of the things we did wrong. I did wrong. Okay, now it seems the list at least has the right length, and it says like 0, 0, 2, 0. 0, 2, 0. 0, 2, 0 is also wrong. It should be 0, 1, 0. 1, 0, 0. 1, 2, 0. 2, 1, 0. What? Okay, so why is the row we are in, the line we scanned? So like there should hopefully be like 3 lines saying 3 lines in the with y coordinate 2. So we have 1, 2, 3. This is actually correct. Yeah, 0, 2, 1, 2, 2, 2. And then we have this one is 2, 1, which is this one, right? The y coordinate is 1, the x coordinate is 2. And then we have 0, 2, 0 is, wait, no, 0, 2, 0 is the one at the bottom. This one is the, is it? X is, yeah, x is 1, y and z is 0. Yeah, okay, so this is actually, this is now true. So this is now the correct set that we read, at least something. Cool. So it doesn't dump the grid correctly, which means something here is wonky. If it's less than min, min and max are all 0 at the start. Like we can fix that, I guess. Oops. Does this fix it? Oops. No, this is the wrong way around. Oops. So the hypothesis is because variables start initialized at 1, at 0, that maybe this logic is broken, but that's not it. If 0, 0, if this is bigger than max, then set max 0 to, this looks correct. This looks correct, right? Does this look correct to you? If it doesn't look correct to you, please let me know. So this should theoretically just find us the minimum and maximum coordinates of, like, of each coordinate, the minimum and maximum that has like an alive cell. And if that is correct, then we iterate over min 2, max 2. Y is min 1, max 1. X is min 0, max 0. This looks kind of correct to me. I'm not quite sure what's wrong. Let's see what it tells me about the bounds. It says the bounds are 0, 0, 0 and 2, 2, 2, 0. So the bounds look correct for the initial grid. But why doesn't it? It contains the correct cells. So that should just be 0 always. Min goes from 0 to 1, and this should go from 0 to 1 to 2. I have no idea what's wrong. Like, it seems the grid dumping is broken, but I don't know why. Oh God. Why did none of you tell me this? Yes, this is much better. Much better. Great. Okay. So now at least like our printf debugging exists and works and does a thing. Let's do a fim.print after .d steps. Just to, okay, it does something. Let's compare these two. After 0 steps, yes, after 1 step. This actually looks okay, doesn't it? Yeah, I mean, I will count that as a win, I think. Cool. Let's just count that as a win and assume that it just works. And so all we now need to do now to do the first, yeah, it's these kinds of bugs, right? Like it's impossible to just, anyway. Now we just need to fulfill the actual question. The number they want is the number of alive cells, right? And so it turns out use a map which has exactly one entrance per alive cell. You can just say number of alive cells is just, let me do a, instead of a, is just the length of the grid. It says 112. Let's check if that is correct. Nope, it's too low. We should actually use our puzzle input and not the test input. Wait, didn't I download that already? I saved it at some point where I have no idea where I saved it. So let's just download it again. This should be correct. Oh, I actually, yes, I saved it here. So now that we think we know what we're doing, and actually, like, this is the 112, great. Could have seen that a second earlier. I have to wait 7 seconds. Okay, so I hope you're all having a good day and you're enjoying the apocalypse. And has it already been 7 seconds? Let's see. Yes, and it's the right answer. Woo! Okay, first part of the puzzle done. For some reason, your simulated results don't match. Yeah, it's always this, right? Like, oh, you did something wrong after all. Don't match what the experimental energy source engineers expected. Apparently, the pocket dimension actually has 4 spatial dimensions, not 3. That seems like an easy thing to fix. Contains an infinite 4-dimensional grid. At every integer 4-dimensional coordinate, there exists a single cube, really a hypercube. Which is still either active or inactive. Each cube only ever considers its neighbors. Yeah, that's exactly the same code. We just need to add a coordinate and something. But now, the initial state of the pocket dimension still consists. Furthermore, the same rules up even though the pocket dimension is 4-dimensional, this initial state represents a small 2-dimensional slice. Simulating a few cycles produces the following configuration, where the result of each cycle is shown layer by coordinate. Yeah, this is gonna be fun. Yeah, I mean, it seems this is just like exactly the same thing, and I think the choice of like our representation, the representation we chose, is already a pretty good representation for that, because I think kind of the thing they are doing here is like, oh, let's now blow up algorithmic complexity by just like adding it. Like, given that our grid only contains a bound given by the number of alive cells and not by the number of total cells, we will care too much. What we do care about is that So I tend to try to, YouTube is complaining again. Let me know if it hangs for you. I don't know. I would just try to soldier on and see what happens. Stream hangs for me, but we will see. Also, yeah, I have another hour, so that's fine. So I try to keep both not